All right, where are we? And what I mean, where are we in the text? Should be somewhere around 326, right? Correct me if I'm wrong. I believe we're still around 326. Sometimes my classes, I'm preparing. Through, and sometimes I prepare through farther than I get, and I go home at night and I think, did we really cover all that? And the only way to really solve it definitively is for me to watch my own videos, and that's scary. Okay, so I don't do that. I just make them and post them, and but if I remember correctly, we were talking about this idea of acids and ionic bases that react to produce salts and waters. Can you tell me from your notes, what was the last thing we did? Where were we? I was boxing and circling. I was aciding and basing, and okay.
The example
So we're working example 9.2 in 3rd edition, which would be what, 10.2, probably in 2nd edition. All right. Let's return to this idea because we've come up with several different ways that we can identify the acids and the bases in a reaction. We've talked about proton donation, proton acceptance. We've talked about, to this point, all of our acids have been covalents. So if we have a covalent and a ionic in reaction, we know that the covalent is going to be the acid and the ionic is going to be the base. We also know that if the formula starts with hydrogens, it's probably the acid. We know that if the other ionic has an OH in it, yeah, that's going to be our base because the OH is going to become water when it accepts those hydrogens. What else did we talk about? If we've memorized the names of the acids, and you look at a molecular formula, and you say, hey, that's sulfuric acid. I wonder if it's an acid. Just listen to yourself. Because the acids have unique naming paradigms, which you're not required to memorize. I would encourage you to memorize. Okay? So the authors of this material, they're going to provide you the names, or they're going to provide you the formulas of the acid when they give you an acid. So if they say sulfuric acid reacts with, and right after sulfuric acid, they're going to give you the formula for sulfuric acid. However, if you already know it's sulfuric acid, you know it's the acid. The bases don't follow a unique naming paradigm. They're going to follow the standard ionic paradigm or covalent paradigm for naming. So the acids are the only ones that are a little bit different in terms of what we're doing right now. Just as during yesterday's mock quiz, say mock quiz because you took it as a quiz but kept it, this idea that if you look at a reaction, right now we're kind of moving from what are the reactants to what do you expect to find as the products. And the first one we're going to deal with here is when you have an acid, again, it's going to be our covalent molecule, and an ionic base. Okay? For the context of this class, the vast majority, if not every time we're talking about an ionic base, what is going to be the ion that's part of this base that should trigger you? What would you expect to find just about every time as at least one of the ions in this base? A hydroxide ion, right? You're going to look for that hydroxide ion. It's going to be some form of in most cases, not every case, but in most cases, there's going to be some form of a molecule there that has a hydroxide ion as part of the overall molecule. That's going to produce a salt and water. And in my encouragement in understanding what a salt is, oftentimes we think of sodium chloride, NaCl, as salt. This is not salt as in the vernacular table, common name salt. This is a salt. An A salt is basically just an ionic molecule. It's a metal and a nonmetal bonded together through an ionic bond. That is a salt. And H2O. So we were looking at the example 9.2, and again, not knowing exactly where we were in here, but let's consider hydrochloric acid. It starts with an H, must be the acid. It's called hydrochloric acid. It must be an acid. It's a covalent bond. It's probably an acid. Okay, see the different ways of looking at it? And rubidium hydroxide. I have an acid. I have an ionic base, which has the hydroxide ion within it. and it's going to form something and H2O. So the only part I really need to figure out is what is the salt going to be? Right, what I'm going to look for is the two components that are not being in our acid-base reaction. We know that the hydrogen here is going to be donated. The acid is going to donate that, and it's going to connect with the hydroxide here and produce water. Do you see that? The hydrogen and the hydroxide combine to form water. That's pretty much part of our standard. And so we look at what's left over. What's going to be left over after this? Well, remember, we could have taken this and done the ionic decomposition. We could have said, okay, it's HCl plus rubidium ions plus hydroxide ions react to produce a salt and water. But kind of skip that step now, because now that we know we're going to take this part and this part out, and this is our pure acid-base portion of our reaction, what's left over? Chlorine or chloride ions and rubidium ions. And those two are going to come together to form our salt. Okay, so when you take the components of water out, what's left over? Rubidium ions and chlorine ions. We know that OH is a -1 charge, so what must rubidium be? It's going to have a +1, right? Because this had a -1. And together they form that neutral ion, or that neutral molecule. And over here, when we lose the hydrogen, we have chloride ions. And the chloride ion, it's a column 7 element, it's going to have what kind of a charge? It's going to 1 negative, right? So we look at this and see, hey, this is going to 1 positive, this is going to 1 negative. What's their relationship going to be to each other? 1 to 1. Which one of these is the metal? Rubidium. So it's going to lead in the naming, right? It's going to be rubidium, chloride, and it's a 1 to 1 relationship. So this is the formula, rubidium chloride. Okay? So the non-hydrogen portion of the acid combines with the non-hydroxide portion of the ionic base to form the salt. The next part of the example says, write the chemical equation, and I really appreciate, I can see you guys are taking notes, but I also see from some of your eyes that you're getting this, okay? This is not like towards the middle of last module where a lot of you are going, I'm seeing a lot more of, okay. So I want to encourage you, if you're not getting this, seek out help now. Ask questions now, because your peers are getting it. I can tell from some people who normally don't get it until the last minute that they've already got it, which is encouraging to me. Second example, write the chemical equation that describes the reaction between sulfuric acid, notice, between sulfuric acid, and they give us the formula because you don't have to memorize it, though I would encourage you to. That's an H2SO4, sulfuric acid, and sodium hydroxide. Okay. What does it produce? Go ahead and put it in your notes. Don't say it. Put it in your notes, and I'll do it up here on the board. Do it ourselves? Yep. Just do it for your own benefit. It's not a quiz. Just write it down in your notes. You've got a sulfuric acid and sodium hydroxide. It's going to produce something. What is it going to produce? And a reminder to you, after you figure out what it produces, go back and make sure that it's balanced. It's one thing now to say, okay, it's going to produce this and this, and you can decipher what both of those are going to be relatively quickly. Now check it for balance. So we're looking for the balanced reaction equation for this acid and base combination. Okay, so as I just encouraged your classmate, don't necessarily worry about balancing it right now. Look over here and say, hey, what would I expect to find? What would I expect to get based upon the components I'm looking for here? Then after you write down what you would expect to get, go through and count up your subscripts and your coefficients and see if it's balanced. If it's not balanced, balance it. Okay, so you should have a pretty good head start, if not be done. But all right, so not worried about balance now. What generally do we know we're going to find from this? We have an acid, right? And we have what kind of a base? It's an ionic base. It specifically has a hydroxide ion in it. So we're going to expect to get a salt and water. That's the first step. We're expecting to find a salt and water. In the neutralization of the acid and base in that reaction, we're going to form the water. And the leftovers are going to form the salt. So let's look to our two reactants, in this case our acid, sulfuric acid, and sodium hydroxide, our base. And let's see if we can take these apart and form water, and then take the leftovers and form the salt. All right? So, looking over here to sulfuric acid, what do you expect that this acid is going to donate? How many? 2 hydrogens. This is a diprotic acid. It's a polyprotic acid. It's specifically a diprotic acid. It means it's willing to give up both of those and leave behind a sulfate ion. Okay? And what else are we going to combine with these hydrogens over here? The hydroxide, right? Remember, it's going to be the same thing every single time. The hydrogens from the acid and the hydroxides from the base are going to react to form water. Now we deal with the leftovers. We have sodium ions, and we have sulfate. What are the charges? Okay, hydrogens here, or hydroxide we knew was a -1, sodium we know is a +1, right? Hydrogen here, okay, when we lose these 2 hydrogen ions, we're going to have a negative sulfate. What's the charge of sulfate? Should be -2, right? Or 2 negative? Because it has 2 +1 hydrogens. Okay, but right here, this isn't, backtrack just a minute. This isn't a ionic bond. This is a covalent bond, right? So when we lose these hydrogens, we're left with a sulfate. We understand the sulfate's going to have the -2 charge. Okay, so at least in terms of our building blocks, we've accounted for everything. And we know that these two are going to combine together. The 2 remaining components, after the acid base neutralizes into water, leaving these ions behind, and they're going to form a salt, which we now know is going to be sodium sulfate. Now that's a formula, just taking the SO4 and the Na. How would they combine together? What kind of relationship? Is it a 1-to-1 relationship? No, it's not. Because I've got a -2 charge, I need to balance it with positive charges. How many do I need? 2 of them, right? So it's an Na2SO4 molecule that's formed. So my salt is sodium sulfate, which looks like that. Now let's do a walkthrough and see how we are doing in terms of balancing the equation. Okay? Okay, if I've got, I like to look at the salts first. They make more sense to me to do those first, but let's look at them. There's a sodium and sulfate. In order for me to combine 2 with 1, what must I do in terms of the coefficient here to start balancing? I need 2 sodiums, right? How am I going to get 2 sodiums from sodium sulfate? Or excuse me, sodium hydroxide. I need to have 2 molecules of this. Remember, in this phase, I'm only dealing with coefficients, not subscripts. I'm not going to change the molecules now. I'm just going to change how many of them I have available, and I do that by changing coefficients. So I get 2 sodiums from doing this for every 1 sulfate, and that gives me my Na2SO4. Now, we look back and say, how many hydrogens are donated? 2. How many hydroxides do I have available? Well, I only had 1 before, but now I have 2. And guess what? They combine together in a 1-to-1 to form H2O. So this is now my balance. I have 2 and 2, because of the coefficient, to make H2O. How many H2Os do I make? If I have 2 hydrogens and 2 hydroxides, it's going to make 2 waters. And I have 1 sulfate and 2 sodiums to make 1 sodium sulfate. Checking it real quick. H2SO4 plus 2 NaOH reacts to produce Na2SO4 and 2. Yes, we're correct. Yes, ma'am.
I'm confused where the subscript 2 after the Na came from.
Okay. Sulfate is a polyatomic ion that has a -2 charge. Okay. Sodium is a column 1A element. So its ionic form is a +1 charge, right? So if you've got a -2 and a +1, and we need to have a neutral charge, we need to bring them together. They're going to come together. Two ions with a 1+ each to give 2+ to balance the 2 negative. So sulfate here, the sulfate's going to come across with 2 negative. It has the ability to bond with a 2 positive or 2 1 positives. Sodium is a 1 positive, so it can take 2 of them and balance the charge. Because if we look at SO4, let's pull this out to the side. SO4 has a charge of 2 negative. Our sodium has a charge of 1 positive. If I bring this sodium and this sulfate together, the overall charge is going to be 1 negative. If I, however, bring another sodium to join the party, now I have 2 positive, 1 positive plus 1 positive is 2 positive, and it bonds with a single 2 negative to form a neutral molecule.
So we're going to need to have the charges memorized.
Yep, from the polyatomic ions, yeah. You might be able to figure out from here saying, hey, I'm losing 2 hydrogens, my charge is changing by 2. You see? My charge is going to change by 2. But technically this isn't an ionic bond, and so you really do need to know the polyatomic ion charges. This one is easy. This is an ionic bond, which means I can get my charges straight from here. It's pretty intuitive. This one may not be as intuitive. If you look at example 3, or the third part of example 9.2, is it the same in the second edition, where it has HNO3 plus ALOH3 reacts to produce ALNO3 sub 3 and H2O. But it's the same basic thing. Just take a look at it, and you've got a hydrogen donator. The trick here is, again, the charges. What is it going to look like when it's balanced? I'm going to go ahead and write it on the board. I was hesitant to, but let me go ahead and do it. There might be some advantage in seeing it on the board. Olivia. Okay. Okay, what's going to be produced here? We have an acid, we have an ionic base. It's going to react to produce a salt of some kind and water. Let's deal with the formation of the water first. We expect to donate a hydrogen from the acid, and we expect to donate the hydroxide from the base, and those come together to form H2O. We see our polyatomic ion and aluminum. Okay? And they're going to come together to form our salt. Our salt, The metal part's going to come from the base, right? Because we're donating away from it. This is a negative. This is a positive charge. Meaning this is going to be our metal. And that part's going to come first in our naming. This is going to become aluminum. And for now, I'm going to write it like this, NO3, right? So we've got our pieces together. All the pieces have been counted for. Now we need to go back and look through balancing. The charge, okay, negative. The charge here it's negative, but we have 3 of them, right? Because that 3, each one of them being a -1, is going to balance aluminum, which is a 3 positive, correct? Aluminum's a 3 positive, and we've got 3 1 negatives to balance it off. All right. And we have 3 hydroxides here. So how many hydrogens do I need to donate to 3 hydroxides to make water? I need 3 hydrogens added to 3 hydroxides to make 3 waters. How do I get 3 hydrogens from my acid? Coefficient of 3. Now I've got my 3 hydrogens. They're going to combine with my 3 hydroxides, and they're going to produce what? 3 waters. Okay? My 3 hydrogens react with my 3 hydroxides to produce 3 waters. Now I've got my aluminum. I've got my 2 components to my salt, right? Look it over here. I've got a plus, 3 plus, right? And I have a 1 negative. So how are they? But I've got 3 of them, right? Right? So let's look at what the ideal relationship would be here first. Aluminum, remember we looked at that. It still has a 3 plus. We looked over here. This has a 1 negative. Okay? How many ideally would I have to appropriately form this molecule? 3 of, right, my polyatomic here. I've got 3. That would give me a total for this combination of 3 negative. My 3 negative here balances my 3 positive here. This is the correct formula. Remember, it's an ionic. It only can form in one way based upon the charges. Let's see if our amount are correct. I have 3. I need 3. Good. I have 1. I need 1. Good. We're balanced. Deep breath. Okay. Yeah, we're baby steps. Yes, ma'am.
Hold on, why did you just put the other 3 behind there?
Okay. Because aluminum, same issue we had with the last question you had, okay? We have aluminum, which in its ionic form, it takes on a 3 positive charge. It's going to lose 3 electrons and drop back to the next valence shell level, right? It's going to lose 3 before it fights to gain 5. So it's going to have a 3 positive. It's going to launch those 3 electrons.
Oh, and that has a 1 negative, so you just switched the. Okay.
Right. Each one of these has a 1 negative, so I need 3 of them to give me an overall 3 negative. And then when I have 3 negative and 3 positive, my overall molecule is a net neutral molecule. Okay? And that's the only way the aluminum and our polyatomic here can come together and form this molecule. They only come together in a 1-to-3 relationship. They can't form a 1-to-4, they can't form a 1-to-2, they can't form a 1-to-1, they can't form a 1-to-5, they can't. This is the only way they come together because this balances the charges. And again, make sure we've consumed up all of our reactant to form all of our product. We have 3 and 3 makes 3. We have 3 and 1 makes 1. We've used up all of our building blocks and produced all of our product, and it's balanced. Yes, sir?
Where'd you get 3 H2O?
From 3 hydrogens here, and we had to have 3 hydrogens because we have 3 hydroxides. Okay? Every water, remember, water can be written like this. This is another way to write water. It's not technically correct, but it is a way, is an HOH molecule, right? Remember we did it in 3 dimensions. It's a Mickey Mouse molecule. You have oxygen, and you have hydrogen, and 2 unbonded pairs, right? So it's an HOH. We call it H2O. It's an HOH molecule. It gets the first H. If you think of it this way, you get the first H from here, and you get the OH from here. Okay, if you think of it this way, I get my H from my acid and my OH from my base to form water. Okay, I start with, I added this, right? But my formula gave me, hey, I've got 3 OHs. What do I need in order to make 3 HOHs? I somehow have to add to that 3 hydrogens, right? Where do I get those 3 hydrogens from? Well, they all are going to come from my acid here. I've only got 1 of them. How do I get 3 of them? Add the coefficient 3. Now I've got 3 hydrogens to match with my 3 hydroxides to form 3 waters. Okay? So this 3, which gave me 3 hydroxides, forced me to come up with 3 hydrogens. And in order to use all of these up, I needed those, and they would produce 3 waters. And then all I did was take the bases, or the remaining components and form my salt by taking the metal from the base and adding the remainder of the acid. There'll be a quiz tomorrow, or Monday, unless you want to come in tomorrow and get extra credit. No? Okay. On Monday, from On Your Own 9.4, giving this basic work right here, it'll be based on Your Own. I'm not saying I'll necessarily give you one of the On Your Owns, but it'll be something similar to this, all right? So just be prepared for that. We're going to move on now to the next section, which is, I'm not going to erase all of this because we're going to contrast it. When we have an acid and an ionic base, in most cases a hydroxide base, react together, also known as neutralization, right? We're neutralizing the acids and the bases. The acids and the bases are kind of playing off each other, and the reaction neutralizes them. If it's perfectly balanced, we're going to end up, we have something that's very acidic and very basic, and at the end it's going to be something that's neutral because it's going to be neutral water and usually a solid that precipitates out or stays aqueous, but it's neutralized when it's perfectly balanced. Now we're going to move into a different kind of relationship, and that's the reactions between an acid and a covalent base. An acid and a covalent base. And the example they give us here is, we're going to be looking at NH3. Okay, and they talk to you in the beginning of this section. It's kind of helpful, but this is page 328 in 3rd edition. The reactions between acids and covalent bases. And it's the same concept. We're going to be losing a hydrogen that's going to bond itself to the base, but it's going to look a little bit different than what we're used to. We're still going to lose a hydrogen and still going to gain a hydrogen, but how does it happen? Well, again, looking at NH3, they give us from the book our old familiar 2-dimensional NH3. But because we're so sophisticated now, we can draw this in 3 dimensions, right? We look at it and go, oh, I recognize that's a pyramidal. That's like Slim Jim right here, right? It's a pyramidal. I have 3 legs to this tripod. My nitrogen is my top of my tripod, and I have a hydrogen, and I have, let's see, I'm going to do it like this. I have my unbonded pair, and I have a hydrogen, and I have a hydrogen coming forward, and I have a hydrogen going back. So I've got a tripod. This, if you wanted to draw it this way, you could, maybe a little bit like that. Okay, so that's in the plane. I'm looking at this base, and again, because we're so sophisticated, I'm going to erase the 2-dimensional Lewis, and we'll stick with the three-dimensional geometry right here. NH3, if I use this as my base, I'm going to use this as an example of a covalent base. Okay. If I have an acid, say HCl, my acid, hydrochloric acid, is looking to do what? As an acid, it's trying to donate a hydrogen, right? Okay. So we're used to this idea of having a covalent bonded acid, hydrochloric acid, and we still recognize that there's going to be a separation of that hydrogen to react in some way with the base. When this hydrogen comes off of there, what is the hydrogen trolling for? What's the hydrogen ion looking for? What does the octet rule tell us about hydrogen? What does it want in its valence? Does it want 0? No, it wants 2. It wants 2. And in the environment that we're putting this hydrogen that's being donated by hydrochloric acid, okay? It's a monoprotic acid. It's giving away 1 hydrogen. That hydrogen is looking for 2 electrons. Okay. Let's look over here at our NH3 molecule. Is the NH3 molecule satisfied with its octet? It isn't? Is this a neutral molecule? I mean, is it satisfied? How many electrons does this hydrogen see? 2. This one? 2. This one? 2. The nitrogen? 8. Its octet's satisfied, right? It's fine where it is. Think of it this way. This hydrogen out here, it has no electrons. And it's walking around the neighborhood, okay? And it looks over here and sees this NH3 molecule. And what does it say? Like most people that lack maturity, that's not fair. How come I don't have any electrons? And those 3 guys, they all get to share. They all have 2, right? Where can I find myself a couple of electrons to hang out with? Oh. Hey, electrons, what are you guys doing? And what happens is this hydrogen comes on over here and says, you want to share? It really does. I mean, if you listen close enough, you can hear it. So do you see the relationship here? This hydrogen is going to get in here and say, I want to share those those unbonded electrons. This molecule isn't looking for anybody. It's fine. It's perfectly happy sharing these 2, sharing these 2, sharing these 2, and now has 2. Its octet's full. This hydrogen comes along and says, hey, I want some companionship too. I need to come in here. Let's share these two electrons as well. So it's going to be now 2, 2, 2. This hydrogen sees 2. Its octet's full. The nitrogen, what does it see? 2, 2, 2, 2. Its octet is full and it's satisfied. And that's what's going to be taking place when we have a covalent base reacting with an acid. Is we're basically going to be adding a hydrogen to the covalent base. Okay? They have this note on page 329 in your book. It says, covalent bases accept only 1 hydrogen ion, only 1 proton. So if you have a diprotic or a triprotic acid, we translate because it may be new. If you have an acid that donates 2 hydrogens or an acid that donates 3 hydrogens, that means you're going to need more of the base to accept that hydrogen ion, okay? The base is only going to take 1 because look at over here. It was satisfied before, and it was satisfied because it had an unbonded pair. It's willing to take 1 freeloader. These are like clowns in the clown car, right? It can fit 1 more. It's going to fit 1 more in there, but it can't take 2 more. It doesn't have anything more to share. It can't take 2. It can only take 1. So if rather than an HCl were being used, let's say we're using, from the last formula, we have H2SO4, and we see this acid as being diprotic, donating 2 hydrogens. How would I combine that with this base? Well, each one of them can only take 1 hydrogen, and since it's a diprotic acid, it's donating 2, so I need a 2 to 1. I need 2 bases for every 1 acid in order for them to perfectly neutralize, to accept every donated hydrogen. As a matter of fact, the example they use in the book, and I didn't notice this, but they use this H2SO4. They say we've got H2SO4 And we're going to add it to water, H2O. Is water an acid? It can be, but in this situation, it's not. Remember, water is our example of an amphiproduct or amphoteric, which means it can be either a base or an acid. Since we're mixing an acid with it, the water is going to say, hey, I've got acid. Today, I'm going to be a base, and I'm going to neutralize the acid. If I added a base to water, the water would become the acid. So it can be either. In this case, I'm adding sulfuric acid to water, so this is going to be the acid and the base. And in this reaction, what will we expect to produce? Again, we're not balancing yet. We're just looking at what molecules do we have. I've got an acid and a base. This base, water, is a covalent base, right? Acid and a base. It's going to react to produce I'm looking at my base. What is my covalent base going to do for the acid? It's going to neutralize it by taking on what? It's going to add one of the hydrogens to it. It's not going to break apart. It's going to add the hydrogen. If I add a hydrogen to H2O, what do I produce? H3O. Heavy water, hydronium. And hydronium has a +1 charge. And what's left over? Everything here has been used up. I take the base, I give it another hydrogen, and I write it again. What am I lacking? Well, the acid has lost its hydrogen, and so I'm left with SO4 ions. And this has a -2 charge, right? So, now let's go back and balance the equation. My acid is a diproduct acid. It's donating 2 hydrogens. My water can only accept 1, so how many of them do I need? I need 2 of them so that every molecule can accept 1 of the donated hydrogens. And then because I start with 2, and all I do is add a hydrogen to it, I also then have to produce 2 hydroniums. And looking over here, I only have 1 sulfate and 1 sulfate. So, as a general rule, what do you see? What's produced? Well, if we have an acid and an ionic base, specifically a hydroxide base, reacts to produce a salt, which is a metal-nonmetal ionic bond, and water. When I have an acid and a covalent base, it produces ions. Produces the ions. We would have had ions up here, but those ions came together to form salts. Here, these are going to be ions in solution. Yes, Gino? 2 for the H2O. I needed 2 waters because each water can only add 1 hydrogen, right? And my acid here is going to give me 2 of them. In order for me to use up 2 hydrogens, I have to add it to 2 bases. So these 2, if I didn't have a 2 here, I would still have an extra hydrogen ion floating around, or an extra hydrogen looking for a home. But by giving it a 2 here, I can consume both of those. But that still leaves me with an SO4 ion, which is why it's only 1 of them over here. So again, if we did it using the blocking and things I used before, you can think of the hydrogen here as combining with both of those, 2 and 2, to produce 2. And then I'm left with my ion. There. From the book, quoting, it says, in the previous section, a covalent acid react with an ionic base to form an ionic compound and a covalent compound, salt and water. In this kind of reaction, a covalent acid reacts with a covalent base to form two ions. And of course, they encourage you to look at on your own 9.5 and 9.6. Let's look at example 9.3 before we finish for today. Example 9.3. Says, what reaction occurs between H3PO4 and ammonia? It says which reaction occurs between H3PO4 and ammonia, which is a base. Which is a base. Okay, you probably could have recognized this as the base anyway, but this one has hydrogen leading. You probably would have assumed it was the acid anyway. Okay, so we have an acid, and what kind of a base? Is this an ionic base or is this a covalent base? Covalent base. So we're following this example here. The acid and covalent base, meaning we're going to expect the hydrogen to add one hydrogen each to the base to produce ions. What's that going to look like? Well, we have 3 hydrogen ions. It's a triprotic acid. It's going to donate 3 hydrogens. So Gino, we're donating 3 hydrogens. Each one of these can take 1. So how many do we need to use up all 3 of them? If this can take 1, and I've got 3, how many do I need? Pardon? Try again. We need 3 of them, right? We need 3. I've got 3 hydrogens. Let's say I have, 3 cards, right? I can only give 1 card to each player. If I want to give up all 3 cards, how many players do I need? 3 players. Each one gets 1 card. Same way, I have NH3. I need to use up 3 hydrogens. How many do I need? Each one can take 1, so I need 3 of them. Each one of them taking 1 to use up all 3. That's the rule. That's the covalent base rule. It takes 1. Always takes 1. So this triprotic acid, or polyprotic acid, H3PO4, and the covalent base of NH3, if I didn't do this balancing now, I'd have to do it later. But hopefully you're seeing it now. Hey, each one of these can take 1. I've got 3 to give away. I need 3 of them. Now, what we expect to produce, we're going to produce, we take our base and add a hydrogen to it, which means NH3 becomes NH4. Add a hydrogen to it. Okay? By adding that hydrogen to it, we started with 3 of them. We take all 3 of them and we just add 1 hydrogen to each one of them. There we go. So this and all of this combine to produce this. What's left over? My PO4, my polyatomic. I don't lose it. I still have to include it in my equation. But that's the product of reaction now. The hydrogens from my acid combine with my base, with 1 hydrogen added to each molecule of my base, to form an ion, and then the remaining ions get carried into solution as part of my products of reaction. They also give the second example of, let's see, H2Cr2O7 plus H2O. Okay, my acid, is it monoprotic, diprotic, triprotic? What is it? Diprotic, right? I've got 2 hydrogens. I'm giving away my 2 hydrogens. To give away 2 hydrogens, and in this case, remember water is amphiprotic or amphoteric, it's going to accept 1 hydrogen per molecule. And I need to give away 2, so how many do I need? I need to have 2, okay? Which means my 2 of my covalent base and my 2 hydrogens are going to combine to form 2 hydronium. Okay? And what's left over? The second part, the second half of my acid is left over, right? It carries forward as a product of reaction.
It's 2 negative. Yeah.
Yeah, review your polyatomic ions. That's going to be a good thing for us to do here, right? But you should see it. Each one of these is a +1, so 2 negative. Okay. So basically what we have is the hydrogens are bonding to the base to form an ionic molecule, and the leftovers from your acid are being carried forward as an ion as a product of reaction. So examples, on your own 9.5 and 9.6 cover that section as well. So I would encourage you in the mix to look at on your own 9.4, 5, and 6. We have just a couple minutes, like less than 5. You have a question?
No, I was just wondering if
Okay.
we were going to do it on your own.
No, we're not going to do them right now. No. I mean, you can't, well, I want to introduce a concept, which is the next segment. We're going to actually teach it next time we get together, next Monday. The molarity, idea of molarity. Everybody done with this? Pardon? Yeah. Moles are now part of your language. Moles never go away. You recognize from the word molarity that moles were involved, right? Molarity. Mole. It's not gerbilarity, it's molarity. Yo. Water. It's just water. When you drink, here's the deal. When you drink water out of the drinking fountain, you are drinking H2O and H3O.
Are you neutralizing your stomach acid when you drink water?
You're affecting your acidity when you drink, but not because of the pure water, because of the,
I'll try to explain.
you know. But yes, I mean, here's the deal. When you drink water, water is either an acid or a base, right? Whatever environment it finds itself in, it's going to tend towards neutralizing it. But more specifically, too, we're also going to talk. Yo, I haven't finished discussion. This is important stuff. The idea of neutralizing with water, and we also have the idea of dilution with water, which is where molarity comes in. This next topic we're talking about right now. So if you think of your stomach as being an acid, you're pumping hydrochloric acid into the food that you've eaten, and digestion is taking place in your stomach because of hydrochloric acid that's being released by your body on the food you've eaten. That's why when you start to throw up, or when you throw up and it burns your throat, that throat burn from barf is hydrochloric acid from your stomach burning the lining of your esophagus, because your esophagus does not have the right kind of material to protect you from hydrochloric acid. Your stomach does. Acid reflux is hydrochloric acid burning. It can. It's acid. It'll burn away the pink material, right? It won't neutralize it, but it'll dilute it. And that's what we're going to talk about here, dilution. Okay? So, when you have acid in your stomach, we'll close with this rather than molarity. When you have acid in your stomach, and you then take an antacid, what do you suspect the antacid is? It's a base. It's calcium hydroxide. When you take Tums, you are eating calcium hydroxide. When calcium hydroxide reacts with hydrochloric acid in your system, reacts to produce, right? You're going to make water and calcium chloride. Calcium chloride. And when doctors tell you you need more calcium, sometimes they say take an antacid. Why? Because in the reaction it'll neutralize the acid and give you calcium chloride in your stomach.